Hello, welcome to my fourth video on Introduction to Constraint Logic Programming through Picat. Today we are going to write some recursive functions and predicates on lists and trees. Let me first warm you up by showing you some of the built-ins on lists. Alright, so let's create a list. 1, 2, 3. And so a list is a singular linked list. Okay, you can add an element at the beginning of a list, all right, in constant time. So for example, we want to add a 0, okay, to x. And a complete list, it's not easy to add an element at the end, okay, of a list. So what we could do, for example, we want to add 4 to the end of the list x. What we could do, we could use concatenation. Okay. But this operation takes linear time. Okay. So there's a good thing about logic variables. Okay, what you can do, you can keep the tail of a list open. Okay, by saying open, I mean, okay, so by having a variable, okay, a variable tail. And in this way, you can add elements at the end, okay, of a list. Okay, so for example, so t equals, let's say we add 4, okay, then another t, okay, and t1 equals 5, okay, t2. Okay, in this way, okay, we can add elements at the end of a list in constant time, right? So that means, okay, okay, this is inherited from Prolog. Okay, so that means we can have an efficient data structure like a stack and a queue. Okay, so because you can add elements at the beginning in constant time and add an element at the end also in constant time. Okay, we will have several examples. Okay, using stacks and queues. Okay. So let's take a look at some of the built-ins. Let's say we have a list, and the first function. Okay, let's call it y equals first x. All right, and the function last. Okay, retrieves the last element of the list. Okay, remember this function last because in order to get to the last element, okay, it needs to start from the beginning, so it takes linear time. And we get the length. All right, get the length again. This length function takes linear time. Okay, we can get a sum up the elements in the list. All right, and we can sort. Okay, we can sort the list. All right, sort. Okay, the list already sorted. We can sort down. Okay, in non-increasing order. Okay, so we can do reverse. Okay, we can also check if it's sorted or not. Okay, is it sorted or not? Oops, sorry. Sorted. It's a predicate, so we have to it. Okay, it's a predicate, and we can also use this one. Say y is insert ordered. Okay, there is a built-in. So x is ordered list. Okay, let's say we want to add 4 to it. All right, then we get ordered list. All right, so the list is ordered. Okay, and after insertion, the list remains ordered. And there are some built-ins in the utility module. Okay, in order to use those built-ins, we need to import the module. Okay, import. Okay, one of these built-ins is called permutation. Okay, we can use this one, permutation. Okay, so x equals 1, 2, 3, and x. Okay, the permutation is y. All right, so we can generate all the permutations, and we can find all the permutations. There is one called find all. Okay, find all y such that permutation xy is true. All right, then we say ys. All right, so ys, that's a list of all permutations. Okay. All right, good. Now let's see how to define, okay, these functions and predicates. Okay, so let's call it recursive. All right, the first function is called first. All right, first, that's simple, yeah. So the first function, okay, this is the head. Okay, this is the tail. Okay, we don't care. Okay, the first function is, okay, h. And how about last? Okay, last, this one, if the list has only one element, all right, has only one element, good. So let's say x. Okay, then the last element is x. All right, otherwise, okay, so we don't care about the head. Okay, then the last element of tail is also the last element of the original list. Good. Of course, if you give an empty list, if you call this on an empty list, okay, you will get an exception because empty list does not match any of these patterns. Of course, we cannot define these functions because these functions are built-in, so we have to rename it. Okay, let's say my. All right, next let's say my length. All right, my length. Okay, this is a list. This is okay. Take a list. Okay, we say length. Okay, this is a length. All right, let's do it. Okay, okay, using recursion. Okay, so my length, it takes a list. All right, and the accumulator, okay, is 0, and then the length. All right, so basically for this one, if the list is empty, all right, ACC, okay, len, what do? We just, all right, bind len and unify len and ACC, okay. And if it's not empty, then it has a head and a tail, but we don't care about the value because we are just counting the number of elements. All right, say tail, ACC, len, and then we can reduce this code to, okay, my len t ACC and then len. Okay, this one we add 1 to the ACC. For each element we add 1 to it. Okay, that's my len. All right, let's define my sum. Actually, my sum can be defined in a similar way. My sum L, okay, initially the accumulator is 0, and okay, the last value, the final value is sum. All right, so if the list is empty, ACC sum, and then we say sum equals ACC. And this is the head, tail, ACC sum. Then what do? Okay, we just reduce this code to T and ACC plus H, and then sum. Okay, good. All right, next, let's consider my reverse. Let's create my reverse L. Okay, actually, we follow the same pattern. All right, so let's say this is a reversed list. All right, then what do? My reverse. This is L. Again, we start with an accumulator. This accumulator is like a stack. Okay, a stack. Okay, in the beginning, the stack is empty. All right, the final result is R. All right, and if the list is empty, all right, this is ACC, and this is R. ACC is a stack. Okay, then we just return the stack. Okay, stack is a list. All right, but the order is reversed. Okay, ACC, and this is a head, tail, ACC, and all. Okay, this is like a stack. What do we do? Okay, for each element, we push it. Yeah, push it to the stack. Okay, so reverse T and push it to the stack. Then okay, so we add T to the front of the accumulator, and then R. Good. That's my reverse. All right. Next, let's consider an example that uses queues. Yeah, let's consider this one, separate. All right, separate. Okay, so it takes a list and it divides the list into two partitions. Okay, the L1 and L2. All right, so L1 okay consists of let's say odd indexed elements, and L2 consists of even indexed okay elements. Good. So let's do this. So L1, L2. Okay, this time there are two queues. Okay, so if the list is empty, then okay. If the list is empty, okay, I think it's better to do this way. Okay, to do it this way. So if okay, let's say this X and Y. Okay, this is a tail. So what do? All right, we say L1 equals, we add X to the first queue, L1, good. L1, the rest of the list is a variable. Okay, we keep it open, all right? So called L1R. L2, and we add Y to the second queue. So to the second queue, okay, so it's LR, and then we keep going. Yeah, we keep going. Okay, so this is L1R, L2R. All right, if the list does not have two elements, okay, that means it has a single element or it is empty. Okay, then what do we do? Let's say this is L. Okay, then we just say L1 equals L and L2 equals empty. Okay, so okay, in this way we can divide this list into two partitions. Okay, you can see this example. Yeah, we can keep adding elements at the end of the list. Okay, what do? We okay keep the tails. Okay, keep the tails open. Yeah, and at the end we close. Okay, the tails. All right. All right, let's consider sort. All right, sort. Okay, this is sorted. There's a built-in sorted. Let's say my sorted. This is sorted. So this one takes a list, and it succeeds if the list is sorted in non-descending, okay, non-descending order. All right. So if the list has two elements, X, Y, okay, T, then what do? Okay, it is sorted. All right. Let's say the elements are numbers. Let's say okay, the elements are any terms. Okay, then we can use this operator. So we can use this operator. Okay, this operator applies to any terms. Okay, if you use it without the ampersand sign, this one only applies to numeric terms. Okay, this one okay can be applied to any two terms. Okay. So and then the tail is also sorted. Okay, so the tail is sorted. I mean the rest of the list, including Y, is sorted. Well, of course, and otherwise, okay, otherwise that means the list has only one element, or it is empty. Okay, then it is sorted. Good. Well, of course, this one sorted. Okay, you can see. Okay, this is a list. Okay, this it rebuilds in order to test if it is sorted. It rebuilds these cons. Yeah, so that is a waste of time, and the compiler is not smart enough to identify these common subterms. So what we could do, okay, we could use this one. Okay, let's say this is an ampersand. Ampersand is called as pattern. Okay, so as pattern. Okay, this is a feature from Haskell. Okay, borrowed from Haskell. This one, okay, it is as pattern. Okay, this is list is as pattern. So L references the tail of the list. The tail, okay, the tail has one Y and the rest of the list we don't care. So okay, then what we could do, we can avoid okay rebuilding this term. So then we can do this, and then this is my sorted. Okay, this is more efficient. All right, good. All right, now let's consider sort. Sort. All right, sort. Okay, this is a built-in. Of course, we cannot name it sort. So let's name it selections. Insertion sort. Let's do insertion sort. Insertion sort. Okay, insertion sort. All right. So what do we do? Okay, we can also make it tail recursive. So list. Okay, this is a sorted list. All right, let's say this is sorted. What do we do? What do we do? This one insert sorted, we define predicate. Okay, in the beginning, the sorted part, okay, is empty. Okay, and the final sorted list is sorted. All right, good. So then this predicate can be defined. I'm sorry, and can be defined this way. Okay, so this is ACC. ACC means the sorted part. Okay, okay, maybe. Well, what we could do, we can say it's called it sorted zero. Okay, this is already sorted. All right, so for each element x, all right, so let's say head tail. Okay, this head tail. So what we could do? All right, sorted zero. We want to add h into the sorted list. Okay, this is a built-in we could use called insert ordered. Okay, so sorted 0 and h. All right, this one becomes, it is a function. Let's say the returned value is sorted 1. Good. And now we recurse. Okay, we recurse on the tail. So using this as a new accumulator. Okay. Good. And if the list is empty, all right, if the list is empty, if the list is empty, okay. If the list is empty, then we are done. Okay, so we return the sorted list. Okay, that's insertion sort. All right, let's consider quick sort. Okay, quick sort, actually we could do something like this. Okay, quick sort, if the list is empty, then the sorted list is empty. Quick sort. All right, then if it is okay, head and a tail, what we could do? Okay, we could do something. We could use list comprehension. We can say partition the list into two parts using h as a pivot. All right, the first part we quick sort. Okay, we partition it. So the first part consists of elements that are less than or equal to the pivot. Okay, so this is element. Okay, and element is in T, and element is less than or equal to the pivot H. All right, and then we call recursion, okay, recursively on this partition, and then concatenate the pivot. The pivot, okay, goes to the middle, and then quick sort. E, okay, this time E is in T and E is greater than, okay, the tail, greater than H, the pivot. All right, so well, quick sort can be done, described easily this way. Okay, this is pretty much like quick sort you can write in Haskell. All right, now let's consider how to define non-deterministic predicate. Okay, there's a non-deterministic my member. Let's call it my member. All right, my member. This is x. This is let's say h. This is tail. Okay, tail we don't care. Okay, make it non-deterministic question mark arrow. So this is x equals h. Okay, and my member. Okay, so the first one says if x and h are equal, then x is a member of the list. Yeah, that's obvious. All right, then we consider tail, and this one is the last rule. So last rule, you don't need to make it non-deterministic because there are no remaining rules. So this is then say my member x is tail. Okay, and we can similarly we can define my select. Okay, so this is very similar. Okay, this is h tail, and the rest of the list is r. Okay, we first. Okay, this is non-deterministic. X equals h, and r equals the tail. Good. My select. Okay, this is x, and this is h, and this is tail, and this is r. Okay, so what do we do? Okay, this time that means x, we don't select the current element h. So what do we do? That means x r goes to the rest of the list. All right, so the rest of the list. Okay, let's say r1, and then we do select. So x and then tail and then r1. Good. So this is my select. All right, now actually with this we can write my permutation. Okay, so it generates. So let's just call my perm. All right, my permutation. Good. It takes a list. All right, and so what do we do? Okay, get a list. If the permutation is p. So the permutation equals, if the list is empty, of course, the permutation is also empty. Yeah. Otherwise, okay, let's say this is, what do we do? Okay, this is a list, this is permutation, and then what do we do? We use my select, okay, to select an element, let's say x from L. This is the rest of the list. And what we could do, this permutation is okay, x followed by p1. Okay, what is x? X is an element, okay, is a selected element from L, and I is the rest of the list. And what is p1? P1 is my permutation. Okay, this is r p1. All right, so that defines my permutation. All right, great. All right, now let's take a look at, let's write some functions and predicates on binary trees. Okay, so the first question is how to represent a binary tree. All right, we can use this one called is binary tree, B tree. Okay, let's say the tree is empty. We use this add-on, okay, to represent an empty tree. Okay, so it is a binary tree. And then otherwise we use an array, okay, an array of 3 elements. Okay, the first one is a value. Okay, the second one is the left subtree, and the third one is the right subtree. Okay, we use an array. Okay, so this one is, if this one is a B tree left and is B tree right, okay, then it is a binary tree. Okay, basically that defines a binary tree. Good. And now let's do count nodes in a tree. Count. All right, of course, if the tree is empty, okay, then the count is 0. Count. All right, so if the tree, we don't care about the value. Okay, left, right, Okay, then we count recursively. We count the nodes in the left subtree, count left, okay, and plus count right, and then add 1 to it. Okay, that's count. Of course, this is not till recursive. Yeah, you can make it till recursive by adding, okay, by writing a help function that takes an accumulator. Okay, so now let's do a in order traversal. In order, okay, it takes a tree. Okay, we want to get tree. Okay, this is a in order traversal. Good. Okay, this is a traversal. Let's say L. L is in order traversal. All right, this time let's make it till recursive. Say in order, it takes a tree and it takes in order traversal. Okay, this time this one we want to use a queue. Okay, not a stack. We keep adding elements at the end. All right, so it is L and in the end. Okay, then we close it. Okay, so this is called a difference list. Basically, the idea is L minus this list. Okay, forms the traversal of this tree. Good. Use a difference list. So this let's call it LR the rest. All right. But if the tree is new, okay, then with the difference is L and LR are the same. That means the difference is empty list. Okay. In order, okay, it is value, okay, left, right, and then what do we do? L, LR, traversal. And what do? We traverse the left subtree first in order. Okay, left, there's L, and let's say L1. Okay, this means L minus L1, all right, is the traversal of the left subtree. And then we say L1 equals, okay, value and L2. And then in order, we traverse the right subtree. L2 and then LR. Okay, so this is very beautiful. Okay, we use incomplete list as a queue, and we keep adding elements, okay, to the queue. You see, this one is till recursive. Okay, till recursive, and it runs faster. Yeah. All right, let's consider another function. Okay, let's call it, let's say we have a sorted array. We want to build a parse tree. Let's call it array to tree. Array to tree. Good. It takes an array. Good. And it builds a tree. So what do we do? Okay, let's say the array is sorted, and then we want to build a balanced, okay, binary tree. So what do we do? Okay, so we introduce a help function. Okay, let's say this is the ARR. The first index, okay, is 1, and the last index is the length ARR. And this is the tree we want to build. All right. Good. So this is a predicate. Okay, this is help predicate. So what do we do? This is the ARR. Okay, this is one low and high. And this is a tree we want to build. Yeah. We can use if then else. If lower is greater than high, okay, then what do we do? Okay, then the tree is empty. Yeah, tree is new. Else if, okay, is lower equals high. If, okay, then what do we do? Okay, that means if it equals, okay, then tree is, okay, it has only one value. This value is lower, and the two children are new. Good. So otherwise we can do recursively. Okay, let's say middle. Okay, is lower plus high divided by 2, and then we recursively, call this, okay, say ARR from lower to mid minus 1. Okay, we have tree 1, right? Good. Okay, we build a tree 1, and then from mid plus 1 to high. Okay, we build another tree called tree 2, and then, okay, what is this tree? Okay, this tree equals, okay, this is the value is ARR mid, okay, and this is tree 1 and tree 2, okay, do it recursively, and if then end. All right, that's all right, we convert a sorted array, okay, to a tree. All right, now let's consider this. Okay, leftmost. Given a tree, we want to get the leftmost node. All right, so leftmost. All right, good. So the leftmost node, of course, we assume the tree is not empty. All right, so leftmost. So it is leftmost. Okay, if the value, okay, if the left child is nil, all right, then this is the leftmost one. If, okay, it is not nil, that means if you come to here, okay, that means the left child is not nil. All right, so what do we do? Okay, that's left, then we recurse. Yeah, we recurse on this left. Well, similarly, we can have rightmost. Okay, we can have rightmost. Okay, we can have rightmost. Okay, that means if the right child is nil, then okay, this is the value, is the rightmost one. Okay, this is left, this is right, and then recurse. All right, now we are ready to write a predicate to test if a binary tree is sorted. Okay, is a binary search tree. Okay, let's create a binary search tree. Good. All right, sure. Okay, if the tree is nil, it is true. Yeah, binary search tree. Okay, what do we do? Oh, actually, we could do this. It is a tree, and it is a binary search tree. And then what do? We introduce a help function, okay, binary search tree that takes the leftmost of the tree and rightmost of the tree as, okay, as lower and upper bounds. All right, then we continue. Say binary search tree. If it's nil, okay, we don't care about the bounds. Okay, it is always true. Binary search tree. Okay, if this is a value and this is left, this is right. Okay, this one. Okay, let's create lower bound, upper bound. All right. So that means in order for the tree to be a binary search tree, the value must fall in this range. Yeah. So lower bound is less than, okay, and the value is less than the upper bound. And also, okay, the left subtree is a binary search tree, and the right subtree is a binary search tree. So left. Okay, when we recurse down the left subtree, okay, we change the upper bound to value, and when we recurse down on the right subtree, okay, we change the lower bound to value. Good. All right, good. So binary search tree. Okay, as the last example, we want to write a non-deterministic predicate that returns non-deterministically the paths in a tree, a path from the root to a leaf. Okay, so let's say first it returns the leftmost path, and then the next one, and then the next one. Okay, let's consider this path. it takes a tree. Okay, it returns a path. Good. Good. All right. So it returns a path. Okay, if the tree is new, okay, then the path is a tree. The path is empty. Okay, path is empty. Path. All right. Let's say if the path is if the okay, it's a leaf node. Yeah, if it's a value, then the left is new and the right is also new. Okay, then the path contains only this single value. Okay. Okay, otherwise we make a choice. Okay. Right, left, right. Okay, let's say we first go down right, go down left. Yeah. Okay, we make a choice. All right, we go down. Say path equals. Okay, this is a value and path 1. Good. And then we go down left. We go down left, and this is path 1. Good. And the next one is okay, go down right. Okay, the next is like a fork. Yeah. All right, so we go down right. Okay, this is value, and then this. Okay, change this one to right. All right, good. Wow, we have written a bunch of functions and predicates. All right, good. I hope I didn't create any typos. All right, let's test them. Okay. Recursion. Oh, amazing. No typos. Yeah, no typos. Okay, let's say x equals 1, 2, 3, and then first. Okay, my first, is it? My first, x. My first. All right, my last. And then my len. My len is equal my len. Okay, my len. And my reverse. It's called just my reverse, is it? My reverse. Okay, and my selection sort. Selection sort. Selection sort. Oops. Selection. Oh, not selection sort. Insertion sort. We define insertion sort. I will leave selection sort as an exercise for you. All right. Insertion sort. Yeah, but it's already sorted. Okay, let's change it a little bit. All right, good. And quick sort. Quick sort. Quick sort. Yeah. Okay. And next we have this my permutation, my member, okay, my member, okay, let's say ex, okay, let's say 2, 1, and 3, okay, my member, my select, and also the rest of the list is, okay, let's call it R. All right, good. All right, first select 2, and select 1, select 3, good. And now let's check permutations. Okay, go back to 1, 2, 3. Permutation. My permutation x, okay, let's say is p. All right, permutation. Okay, you get all the permutations. Good, good. Now let's build a tree first. Okay, what is a predicate? Oh, it's called array to tree. Array to tree. Okay, so we have this one. Let's call it, okay, 0 to 10. Good. We create an array. That's a list. All right. And then we say array to tree. This is x. Okay. This is a tree. Equals array to tree. Okay, that's a tree. All right. Let's say we count nodes. Okay. C equals count tree. All right. So how many nodes? There are 10 nodes in a tree. And let's get leftmost. Okay, leftmost value. Okay, v equals leftmost value. Okay, leftmost and rightmost. And also, is it a binary search tree? BST. This one is tree. Yeah, it says it is a binary search tree. Sure. Okay, and next we want to enumerate all the paths in the tree. Okay, so path, this is a tree, and path. All right, so the first path is, okay, 5 to 1. The root is 5, the leaf is 1. Okay, so then 5 to 3. Okay, we get all the paths. All right, so good. So in this video, basically, okay, we wrote a bunch of procedures on recursive procedures on lists and trees, and we also learn how to write non-deterministic procedures. Okay, thank you for watching.